Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to the last lecture of this week for the ongoing course on understanding and reducing greenhouse gas emissions, and we are focusing on scope 1 and 2 emission reduction through building design and construction. In this series, we looked at different strategies. We are looking at different passive design strategies, and today we are going to look at daylighting and lighting design as part of this discussion. In the previous lecture, we looked at different aspects of natural ventilation, and we understood that even when the building is going to be air conditioned, allowing for natural ventilation and providing manual overrides will result in significant energy saving and eventually the emissions. In this lecture today, we are going to talk about daylighting, how we can incorporate daylighting into buildings. So, we are largely focusing on the design, building design for bringing in daylight. Then we are talking about different lighting systems and controls, and then energy efficient lighting. Now, I am not going to explain here what daylighting is, we are going further than that. What we are seeing here is how to bring in the daylight. Now, before I start to discuss about this, we clearly understand that the most potent source of natural light is sun. So, sunlight is available throughout the day. Now, it depends upon location to location, geographic location, how much light is available. Now, if you go closer to the poles, say you are going closer to the North Pole, then we clearly know that for a couple of months that are winter months, we would probably see no light, while in summers it is going to be a very long day where the daylight is going to be available for probably more than 15 hours in a day. So, now depending upon the geographic location, we have to select the strategies. What I am telling here is different strategies that can be incorporated to make the interiors more lit, daylit. So, when we are talking about daylighting, the first things that is to be planned is how the fenestration, the windows have to be provided, and where they have to be provided, how much they have to be provided, how do they have to be shaded. So, we are talking about windows first, windows or all other forms of fenestration. So, we have two types of fenestrations. One is the top lighting. So, we clearly know the skylights, the atrium tops as the top lighting, and then we have windows for side lighting. So, we have different types of windows which we will come to. In addition to these windows, the fenestrations, we also have their controls and some architectural features. For example, light shelf here, or we may be having a projection overhang here, or we may also be having a vertical projection, a shading device. So, we will have different shading devices, architectural features could also be there, and then we also have space planning. So, what we are really looking at is that we are looking at a uniform distribution of daylighting. Now, that is extremely difficult to achieve because the daylighting is going to be available only through the surface of the building envelope. Now, here the space planning will come into effect. Now, if you are looking at say a regular window, so what we have probably at different angles. So, if you are talking about winter mornings where the sun is quite low, or winter evenings. So, then we may have, if we are providing window in that particular direction, say probably east and west, we will have daylight penetrating deeper into the space, while during the summer sun we would probably not be getting any direct light, but there will still be a lot of diffused light that will come. Still, there is a limitation up to which this daylight can be penetrated inside the room. So, not more than 15 feet is what we see when the window is large enough and it is well designed. So, there is a limitation of how much this light can directly penetrate, that too specific times of the day. So, what we can do there is we can have some features such as this light shelf. We will come to the light shelf in detail in further slides, but what we are really seeing is we are reflecting the light, the direct incident light to the ceiling, from where it further diffuses and it is a better quality light, plus it is also penetrated deeper, it is uniformly spread. Now, what in this figure what you can see here is we also have the provision of a skylight. Now, this skylight also allows direct light to come in, or we can also have it designed selectively, so it diffuses the light, and then we can also have reflective wall, which will further reflect. The moment it is reflected from a surface, it diffuses, the light diffuses, it is not a direct beam. So, what we get from north side is a diffused light, it will not cast shadow and it will be a uniformly distributed light. So, the intent is to distribute it all over the space. Now, what all do we have to take care when we want to do this? One is where the windows are placed and how large are the windows. Okay. So, now if you can see here, so this is almost 80% window to wall ratio. So, of the given total surface area of the wall that we are seeing here, 80% WWR implies that we have 80% of it covered by glazing. Now, how this 80% is going to behave, how much light is it going to bring? But along with that, we also know that the glazing, this direct sunlight will also bring heat along with it. So, how much heat is also coming along and what is the optimal WWR that we need to provide has to be checked. It can be done through proper simulations, but this is what we have to keep in mind. So, what you would have seen that in extremely hot climates, the arid climates, you would have very small windows, just enough to bring in some amount of daylight, but not large enough to bring in a lot of heat, because heat is a major problem there. While in cold countries, in cold areas, you would find that people tend to provide very large windows, but specially designed windows which will bring in heat, but they will not let the heat escape through that. So, we will come to that too, but we have to design the windows for the place, for the context. So, one is window to wall ratio, which is the most important. The second one is the placement of window, orientation, where are we placing it for daylighting. So, we clearly know that if in tropical climates we place our windows in south and provide shading over it, we would be able to cut off all direct radiation from coming in, but there will be diffused light which will be made available if there is shading over it. If we are providing windows on north side, in northern hemisphere, I am talking about the context of India and northern hemisphere in general, if we have a north glazing on north facade, then there is no direct sunlight that is going to come in. So, less of heat and abundant sunlight, natural light which is diffused. So, there is less of heat coming with it, but a lot of light that is being allowed. This is going to remain diffused throughout the day, morning to evening. We are not going to have direct sun except for in the peak summers when the sun goes slightly towards northeast. So, other than that, we are going to have diffused light throughout the year. East and west will allow us to bring in direct sunlight, but in the also in the deeper areas, because the sun, the altitude of sun is very low, and when we have a window which is facing east, in that case we are going to have a much deeper penetration. Of course, we have to clearly see that the light has a limited range, a limited reach. If we provide a window in east, we cannot expect that it will still travel some 100 feet inside the building. No, it will not. It will still have the limitation which we have just seen. So, this is second. So, one is window wall ratio, how much of the window area, of the wall area has to be provided as window, 1. 2, where do we have to provide the window? Do we have to provide it in north, south, east or west? Also depends on the function. For example, if we are talking about classrooms, especially where studios, for example, I am an architect and the architectural colleges will require studios where we do not want the direct light, because when we are working on the boards, when we are writing, so at that time if there is sun, it will cast shadow and the drawing quality may be affected. So, we want diffused light, but abundant light. So, what we would prefer while designing a building, we would prefer that the studios have a north wall, north facade, and it is glazed largely. So, a lot of light is coming, and then we also have to see where the blackboard or to which side the class should face. Large number of people are right-handed people. There are fewer who are left-handed. So, majority of us will be working with our right hand like this. So, we would want the light to be coming from the left side. So, the studio has to face east, so that the north light does not interfere, or the light coming from the northern facade does not cast shadow, and it facilitates. So, this is how careful we have to be when we design windows. Where do we place them? So, this is the second aspect of it. This is for daylighting that we are talking about. Ventilation, the placement we have already covered in the previous lecture. The third thing which we have to keep in mind is window has double purpose. It has two purposes when we are talking about lighting alone there also. One, that it brings in a lot of light. Two, it allows us to see outside. So, we have two types of glazing within that. We have, if we look at this, we have a vision glazing, and the top part is actually for the lighting. Now, the vision glazing allows people to see outside, and it is only up to the height of 7 feet. So, if we have a window, say from a 3 feet or a 4 feet sill level to a 7 feet lintel, so this part of the glazing is the one which is used for viewing outside. This is called vision glazing, and the one above it is clear glaze, or it is for lighting. So, we are going to only get light from it, and there is no viewing possibility there. Now, why am I telling you this? Because we have to see that this vision glazing is also, this part of the glazing below 7 feet is responsible for bringing in a lot of glare. So, what we can do is, and we do not want that. So, we want light, and if we are providing, consider this section. So, if we have a window, this is 7 feet, this is the window above it. So, this is the vision part of it, and this is the light part of it, and then we have the ceiling. Now, if I provide a light shelf here, and this part of the glazing, this vision glazing is a darker shade. So, it does not bring in that much of direct light and does not interfere with the vision. So, what we will do? Otherwise, you would have seen if there are clear glass on the vision glazing part, then in offices people tend to pull down the blinds. So, people tend to pull down the blinds. Now, that defeats the purpose. It does not serve as vision glazing nor as light glazing. So, what we can do, that we can darken this vision glazing, we can reduce the transparency, the clarity of it, so that less amount of light is brought inside, but people can still view outside. So, this is for vision, while for the lighting, the glazing for bringing in light, we can have absolutely clear glass and a lot of light can be brought to the room through this. So, we can separate between these two. Often we have not considered doing this. We can separate materials, the color of the glass for these two parts of the glazing, and also come up with beautiful exteriors, facade designs using this. So, this is how we are going to design the fenestration as the first step, the design of fenestration, design of space to bring in more and more light. And we do not have to forget the contribution that the skylights, the top lights can make. You can look at the quality of this space, and throughout the day it will not require any lighting, artificial lighting. A lot of our public buildings, you would go and see a lot of airports doing the same, a lot of commercial buildings opening up their atriums, courtyards. Even when we are not viewing through a glazing outside, the presence of a glazing makes the humans feel connected to the outdoors, and it makes the overall space quality as an improved space. So, we have to see that even looking at the sky, which is not really viewing what is happening outside at the eye level, even then it changes the quality, and of course, it reduces the energy consumption for artificial lighting. Two, it improves the quality of the space. Now, light shelf here, So, it is an architectural feature, it is a passive design feature for making the light penetrate deeper. But what are the requirements? So, one, we have to have the light shelf above the vision glazing. If you clearly see here, this is the vision part of the glazing. So, this is the vision glazing. Above it has to be placed the light shelf. If we place it in between, it will obstruct the view, it will obstruct the vision. So, we do not have to do that. It has to be above the vision glazing. That is one. Second thing which is most important is that the upper surface of the light shelf. So, I am talking about this upper surface of the light shelf. It has to be reflective. It has to be light colored, it has to be glossy, so that it reflects almost 100% of the light that is incident on it. We are talking about light. So, when the solar light comes and hits this, it almost 100% of it is reflected back. So, this is the second requirement of light shelf, that this top surface of light shelf has to be smooth and reflective, and it has to be regularly cleaned. In a country like India, where we have a lot of dust in the environment, in the air, so this light shelf, the top surface of light shelf, which is also horizontal, it will tend to accumulate a lot of dust over time. So, it has to be regularly cleaned, it requires maintenance, this light shelf. And the third requirement for this one is that this glazing, which is above the vision glazing, it has to be clear glass, absolutely clear glass. We can have double glazed window with clear glass, we can have triple glazed window with clear glass, but it has to be clear glass with almost 90% of the light that is falling onto it to be transmitted inside. It has to be absolute clear. That is the third requirement. So, one, we talked about the height. So, the first condition is height, where are we placing the light shelf. Number 2 is the surface, the top surface of the light shelf. The bottom surface will not matter much, the top surface is what we are concerned with. Number 3 is the light glazing part of it, which has to be having a VLT, visible light transmittance, as very high. And the fourth feature is a reflective ceiling. So, if we do not have a reflective surface here, this light which is reflected from the light shelf onto the ceiling will not be reflected back. So, we mandatorily have to have a reflective ceiling. We have to have a light colored ceiling and reflective surface which reflects it back further. So, it will diffuse it and make it go deeper into the space. This is what we need when we are designing a light shelf, and it is a cost effective and extremely effective measure to bring in daylight to deeper areas, but it will still have its limitation. So, naturally if the light can penetrate maximum up to 15 feet, with this light shelf we may be able to take it say 10 feet further, but we cannot make it penetrate much deeper. So, we will have to look for other options. For example, we have these tubular lights, okay, or what we know as light pipes. So, what it does is that it will have a dome, a spherical dome, which is made up of a transparent material, sometimes acrylic, sometimes glass, and it will attract throughout the day, it will receive sunlight from all the sides. And inside we have a pipe. So, we will have a pipe which will have highly reflective surface inside. So, from whatever angle the light falls onto it, it will further reflect it, and here we have a diffuser. We have a diffuser which acts like a light bulb. So, there is no electrical system here, it is simply a mechanical device not running on electricity. We just have to shape it in a manner that all the light that is incident is able to be reflected, and then it is supplied inside. If you look at the light pipes or these tubular lights from inside, one may not be able to figure out that this is actually not an electricity fed light, artificial light. It is not natural, it is a passive design feature, but it allows us to bring light into deeper areas. But the limitation with this one is that we can make it, we can use it only in the floors where we have a roof above, or at max we can take it a floor below. But we cannot make it work if we are having a multi-storied building and we say that okay, on it is a 10-story building and I want to install a light shelf, a tubular light for a 4th floor. No, it will not work. So, there are limitations with each one of these passive design measures for daylight that we are looking at, but together a combination of these will allow us to make a large part of the building as daylit. Then we also have systems such as prismatic glass. So, what we have in prismatic glass is that it is a thicker glass. So, between the two sheets we will have the prisms, and these prisms can also be tilted, or sometimes they are fixed, their tilt is fixed. So, what happens is that when the light is incident on this prism, and all of us know that how prisms work, so it will further diffuse the light. So, depending upon the incident radiation, incident light beam, there will be a diffusion of the light to inside. So, even when we have the entire glass, we are talking about vision glazing, the regular vision glazing also, even when it has a direct light falling onto it, it will send it as diffused light inside, and there will be less of glare and less of a direct beam that is going to be there. And when we diffuse it, and we can, it will also be directed to the top as we seeing here. So, we can have the arrangement in such a manner that even without the light shelf, the light is diffused and directed towards the ceiling, from where it can further be diffused to inside. So, this is another option that we have available. Now, if we look at daylighting together, so as I said, there are two things that are coming with it. We are excluding the vision part of it, the viewing part of it. Now, the moment we provide window, we are going to get light, direct sunlight, which brings in the natural light for vision, and we are talking about the heat that is accompanied with this light. So, two aspects are there. Now, for that we have to select the glass material carefully, and this light, since we know that it is only going to be available during the day, we have to compensate it with artificial lighting. We have to complement it with artificial lighting to make the building usable during the night. If we have only daytime use building, for example, schools are only daytime use buildings, there the window design has to be slightly different as compared to a 24-hour use building, for example, a call center which is going to function 24/7. There, since the glazing is going to function or is going to impact the heat exchange more than the duration for which it is going to provide light, we have to do a 24-hour simulation, an annual simulation. There we can clearly know how much of heat exchange is happening because of the glazing, and is it relevant enough, or how much of the wall should be provided as window for providing the daylighting. Are the savings equivalent to the extra energy that we require to remove or provide the heat? So, that is what we are supposed to see. So, we are going to look at the daylighting part of it and the artificial lighting plus the cooling or the heating loads for daylighting. Together we will be able to identify how much are the energy savings and how much is the demand reduction that is coming. Now, to do that, when I say that we have to look at both the heat and light part of it, we have to look at two qualities of this glazing material that we are selecting. We have the visible transmissivity or visible light transmittance, VLT, as we know, and then we have the solar heat gain coefficient, SHGC. So, we are looking at these two parameters. Now, SHGC is responsible for bringing in heat, the heat part of it, or allowing the heat to be lost. It is responsible for heat exchange. The VLT is responsible for bringing in the light. Higher VLT implies more amount of light, higher SHGC implies more amount of heat exchange happening. Now, for extremely cold areas, what do we want? We want to bring in more light and we also want to bring in more heat, but we do not want to release the heat. So, here what we would see that there is an optimum number which we would need. For example, in extremely hot climates, we might want to have an optimum VLT, but very low SHGC. While for colder countries, what we might be wanting is that we have a higher VLT and we also have a higher SHGC, but we will have to control it, we will have to control the heat loss. So, we might have to have selective glazings over this glass which will have high VLT and high SHGC. So, preferably clear glass which has a high VLT and high SHGC with some selective coating is what we are looking at. So, depending upon the context, the geographical location, we will select these glasses. We will come to this discussion in detail in the next week where we are going to talk about material selection. In this week, we are only looking at passive design features. Next week, we are going to look at the material selection, the equipment selection. Now, once we have designed how the space has to be, how the windows have to be provided, how much windows have to be provided, what glazing material has to be given, what are the passive design architectural features that have to be provided, all that is figured out. Now, on top of that, we have to talk about the lighting systems and controls. So, we are talking about artificial lighting plus the controls of them. So, we are looking at daylighting plus artificial lighting together, especially for 24-hour use building. And why? Because lighting is one of the major significant contributors to the heat inside the building. So, the heat inside the building is of course because of the environmental load, because of the people who are there, because we release a lot of carbon dioxide and we give a lot of heat into the environment, and this lighting system is also one of the major contributors to the heat that is inside the building. So, now that depends upon what kind of fixture, lighting fixture we are going to use, and this is what we are going to see, and also the controls. So, if you look at the lighting fixture industry, I would say for sure I am talking about the building industry at large, and within that lighting industry has advanced at a pace like no other industry within this building industry. From incandescent bulbs to LED, they have moved very fast. And if we compare, I am sure all of you know that if we compare the traditional incandescent bulb with that of an LED bulb, and we supply or we require the same amount of lighting, same intensity of lighting, then we require at max 1/5 the energy to be supplied. We save a huge part of energy that is going in. And where is this saving coming from? This saving is actually coming from the amount of energy which was otherwise being converted to heat. So, if we look at the traditional incandescent bulbs, we would see that the output is the same. We are keeping the output as the same in all the bulbs as 1600 lumens. Almost 90% of the energy that is supplied of this 100 watts is wasted, it is converted to heat. So, we are adding for each unit of electricity that is supplied, 90% of it is actually going into the space as heat, and this heat will have to be removed from the space if you want to make comfortable indoors. Now, if you compare that with LED light, we have very small portion of this 20 watts which we require here going as heat into the space. So, and that you would have seen earlier, if we had to remove a bulb, an incandescent bulb which was lit, which was on, we cannot touch it with bare hands, it would become so hot. While LED bulbs, you could very conveniently hold them even when they are on, and this is plus the quality of light is better. If we look at the spectrum distribution of the light, then we would see that LED bulbs today, they give us better quality of light, consuming lesser amount of energy and their life is also longer than the incandescent bulbs if you look at it in hours, burning hours. However, one major deterrent which has been there is the cost that we incur per bulb. So, this is the capital investment that we are talking about, but of course, over the period due to the savings in this operational energy and the quality of light that it provides, we recover that very fast. But the initial capital investment in terms of this LED is significantly higher. So, what we know this as, if we are talking about the LED and for whatever fixture we are discussing about, the number of lumens produced per watt, this is called the efficacy of lighting fixture. So, whenever we are selecting the lighting fixture, we have to look at this efficacy. What is the efficacy of the light per watt? How much light does it produce? So, this is what we have to see when we are selecting the fixture, the luminary for artificial lighting. So, this is first thing that we do after we have designed the space and we are going to complement it with artificial lighting. The second is we have to distribute the fixtures. So, where and how do we mount, how do we place the fixtures so that there is uniform lighting, artificial lighting available inside the space. So, if you look at this particular example, the space has been designed and the way these artificial lighting, these luminaries have been provided is to have the minimum, the threshold illuminance that has to be provided, the lux level that has to be maintained for the given space and for the given activity. So, first step we designed the space and the windows. Second, we select the luminary, and third, based upon the luminary we design the artificial lighting, we distribute it uniformly. Once we have done that, we will add on top of this the controls, the lighting controls. So, we can have normal controls, you have seen the manual switches on and off, so which is the simplest form, but in addition to that we can have multiple other controls. For example, we can have photocell controls. So, you would have seen a majority of the street lights in our country today, they have these photosensors. So, as soon as we have sufficient amount of daylighting available outside, they will automatically turn off, thereby saving huge amount of electricity. Earlier what we had, we did not have those controls. So, unless somebody manually turns them off, these lights would continue to remain on and continue to consume energy, the electricity. So, this is photo controls, and these sensors are now commonly available, these photo sensors, and commonly, for example, the balcony lights, the lights in the porch, the outdoor lights, they can all be connected even in a residence. It is not necessarily that for municipality, street lighting or for bigger facilities, the outdoor lighting has to be linked to this photo sensors, no. And one sensor can control an entire row of lighting, entire series of lighting. It is not necessary that for each light we have to have a separate sensor. One sensor can control the entire system. The second one is the occupancy control. So, if people are there, then the light turns on. If people are not there, then they turn off. So, this is infrared sensors. So, as they sense the infrared radiation which is due to the presence of a living body, the light will turn on, otherwise it will automatically be off. We also have sensors which have overrides. So, we can have occupancy sensor as well as photo sensor. So, even when the occupancy is there, the sensor will not turn on if the photo sensor tells that there is enough light in the space. So, even for indoors we can have photo sensors, we can have the sensors sensing that how much of the light is coming from the windows plus the occupancy. So, it can be multiple sensors put in together. So, we have these controls. Then we can also have dimming controls. So, for example, as the day passes and the evening approaches, the outdoor light reduces, but we do not need to turn on all the lights. So, there could be these dimming controls. So, the intensity of the light, the fixture, it can be controlled. It can be done automatically through photosensor. So, we can have programs for that, which we will come to in the last slide, or we can have just manually control, just like we have for fans. The way we control the speed of fans, similarly we can control the illuminance that we are going to get from the fixture. So, what we actually have seen here is that we have dimmer controls, we have motion or occupancy sensors and photosensors, and we can also have timer controls. So, what we can also do is that there is a timer, just like you have in your air conditioner these days. So, we can set timer that the light will turn on at say 6 in the evening and it turns off at 6 in the morning. So, there is a timer control, and we can change the timers for different seasons depending upon the length of the day, or maybe we can also control it depending upon the usage of a space indoors if we are installing it. So, as a fourth step, we have to have controls over it, over the artificial lighting that we have provided. This is one example. So, what we have here, we using motion sensor. So, it detects the motion, it is the infrared sensor that is there, and sensing from this, it sends the signal to the lighting, the entire line of luminaries that are going to be controlled through it. Timer controls would look something like this, that we will have the specialized control which will give us the time, that for how long the light has to be on, or after how many hours or minutes the light will go off. What I was just mentioning, that we can write programs to override or to control. So, if there is natural light, the lux levels can be fixed, that if we have say 400 lux from outside, then the internal lights would be turned on at say 25% capacity. As it falls down to 300, the internal lights may be turned on to 50%. As it goes further down, it may be 75%, and then be below this, if it is below 100 lux, then we turn them on 100%. Plus, there could be sensors which could be motion sensors, occupancy sensors, or here we are talking about the photo sensors. So, we can actually write programs to control how the lights behave, and all this natural ventilation, mechanical systems of ventilation and air conditioning, the artificial lighting, all of these, they can be put together in the systems which are known as building information management systems, or building management system, BMS. So, there what we can actually do is, taking the input from one, we can control several systems, and that is how smart buildings and energy efficient buildings are functioning these days. So, but whether we have BMS or not, the fundamental remains that we have to have passive designing and the architectural designing in place as the first step. On top of that, we can control these different sensors and automated sensors, automated systems through BMS, and make the building even more energy efficient. So, with this we stop here, and we have discussed the passive design strategies for design, for ventilation, for daylighting. In the coming week, we are going to talk about materials, we are going to talk about the renewable sources of energy that can be added into the building systems, and few more topics which will further help in reducing the energy consumption in the buildings. So, thank you very much for being with me here today. Bye bye, and see you in the next week.